One, I'm going to present my project in heat transfer. It is simulation in the ANSYS with a given object. So first, I'm going to set here the steady state thermal. I'm going to check all the parameters, then we will go to the simulation. First, we're going to make our object. In this case, I'm going to do it here directly in the ANSYS. So we're going to wait for a bit. The scale given should be uh, we'll check the parameter first. The x, y should be accompanied which number you are in the list. In case of me, Barte, number 5. I'm number 5. So the x should be 0.5 meters and y should be 50% of that. So I'm I'm gonna try to figure out what what is the temperature at the 0.25 with this parameter. So we're gonna make it first. Okay. I'm gonna draw it from the center, so it should be in the center. It is an mm, so 500 mm. Then 1000. Okay. Then solid. I'm gonna pull it up to 1000 mm. So that should be it. I'm gonna save this first. Mark the box. Save. So I'm gonna exit this. Then it's checked. Means that our model is already saved. Next, we're going to the simulation software. After checking that model, we have here our model, and we're gonna check all the parameters given. First, the material, we're gonna change it to structural steel. Should be structural steel with thermal conductivity of 60.5 watts per meter degrees Celsius. And mesh, we're gonna mesh this up, and the sizing should be fine dito sa may here and the span angle center. Fine. So fine. Then we're gonna add the temperature. The temperature here should be 25 degrees, and the other side is 500 degrees Celsius. Apply to 25 degrees Celsius. And we're gonna insert again another temperature at the other side with 500 degrees Celsius. Gonna center it a bit. In solution, we're gonna add temperature and total heat reflux. Also mesh. We're gonna solve this first. Mesh. Then solution. Valid geometry. So and make this. Oh, there's no selection of the face. Okay, double check. 25 degrees on the other side, 50 degrees. Mesh, it's already meshed. Then addition of temperature and total heat rate flux. And I hope this works this time. Okay, so we have our result. Here is the temperatures depending on the x-axis and the total heat reflux 57 the minimum and the same with the max. It only have one heat reflux because it's homogeneous and only one object. So we're gonna use that to determine the the temperature in the X25. Okay, so s- here's the result. I'm gonna print this later and send to the G form. Okay, that's the data. Also for the total heat reflux. That's the date I made this. Let me see. So with a given total heat reflux, I'm gonna determine what will be the temperature at 0.25 meters. So let's go here. The square is equals to 57 475 watts per area. So I'm gonna determine the temperature with the formula of Q is equals to change in temperature over RTH, which is equals to T1 and let's say TT for Chedoro. That sounds T, TB, TA, TA. And X over the K in the area. So to find Q, I just multiply this by 1. It will be the same. Q is equals to 57475 watts. I'm gonna move it here. Mhm. Let K is equals to 60.5 watts per meter degree Celsius squared. Let me check that a bit for a quick check. Here are the materials. First here. Okay, 60.5. I'm correct. Then our T1 is equals to 500 degrees Celsius. Our area will be 1 meter squared. And our x will be 0.25 meter. And W here is W. I'm just gonna plug input the numbers. 57475 watts is equals to 20 degrees. So minus Ti and 0.5 and 25 meter over K 60.5 watts per meter degree Celsius and 1 meter. Screw. And the TA should be calculator 7 or 75 0.25 over 60.5 1 meter is equals to 237 minus 500 262.1 times negative 1. Okay, 262.5. They should be 262.5 degrees Celsius. This is the temperature temp at x is equals to 0.85.